And without any further ado, I'll introduce Dr. Gary Schwarz. He's the director for our Case Comprehensive Cancer Center. He has had an illustrious career. He has been at Memorial Sloan Kettering, Columbia University, and he came over to Cleveland around 2 years ago. And he has had several initiatives in clinical research in cutaneous oncology, especially melanoma. So, Dr. Schwarz, please welcome.
Hey, everybody. So as Hank was saying, I'm the about 2.5 years now. So I'm at University of Memorial Sloan Kettering Cancer Center. I'm the director of the Case Comprehensive Cancer Center. Not familiar with Case. The Comprehensive Cancer Center actually integrates two hospital systems with Cleveland, both Cleveland Clinic and University Hospital, as well as Case Western Reserve. So all the science that comes out of the university programs and the two hospitals comes through the Cancer Center, as well as any innovations in medical care, medical research. We also work with the clinical leaders at both hospitals to make sure that patients have both EUA completed plaque have access to the latest advances in cancer medicine. So my background is in melanoma and sarcoma. I actually continue to treat patients with both diseases, more sarcoma these days than melanoma. In fact, I'm the only oncologist in Cleveland that has privileges at both University Hospital and Cleveland. So you can see me at other center. It's a novel paradigm with oncology will one day pick up. But I was there at the very beginning, when melanoma was a horrible disease. Still not a good disease for many patients, but there was a time that good melanoma, an advanced melanoma, was truly a lethal disease for all patients. So what are the advances that made the difference? Okay, so where did it all begin? I think there are two seminal, I just want to review the historical perspective of how we are probably today, And I think there are two really seminal advances that over the last 15 to 20 years. And the first is the concept of precision medicine. That is, can you take a tumor and take the DNA of the tumor, and can you put it into a machine, sequence it, and find genes that are responsible for cancer growth? Well, 15 or more years ago, this was really just a fantasy, science fiction, some would say. The first actually person ever done was Steve Jobs from Apple. He had a very rare form of cancer, and he insisted that his DNA be sequenced. At that time, it took 12 months. It was about $1 million to sequence his DNA. Today, we can do this in 7.2 seconds, and it costs about $50. Now, your insurance company will see $2,000 to $3,000 on the bill when you get it done, but it's really very inexpensive today and getting cheaper all the time. So how did that help us? Well, it helps in melanoma, because melanoma is actually not one disease, it's many diseases. And the top here is a more classical melanoma. That is the one that arises from sunburn. And that melanoma is, when we sequence those patients' tumors, they have this mutation in a gene called BRAF. We'll talk a little bit about that. And there are also gene mutations in the other ones called KIT and RAS. In the middle three, there are tumors from melanoma that are not sun-related. So you can get melanoma from areas where there's no sun. You think of sunburn as the cause, but actually you get melanoma from chronic skin damage, a little different, but from areas that are sun exposed. In the middle panel is actually melanoma arising in the mouth, but you also get melanomas in the bottom of your feet and the palms of your hands, under the nail bed. No sun, very little sun. So what makes those different? Well, if you sequence those, they have BRAF, but they really have a major new gene called KIT, 30%. Very different than the skin ones. In the very bottom panel, there's a form of melanoma that arises from the uvule, the eye, called ocular melanoma. I'm not going to talk about that today, but that is a gene mutation, not BRAF, not KRAS, not KIT, but something called gene acute gene 11, a very different mutation. So we made major advances in trying, now that we've identified these mutations by sequencing, can we develop drugs or therapies that block them? Because these are oncogenes. They're the engines of the cancer cell. When you have them in the tumor cell, they're not hereditary. These aren't genes you pass on to your kids. They're there from some sort of environmental insult. Now, the most common then is, from the sunburn. Because UV light is actually one of the most potent carcinogens known to man. That's when we talk about sunscreen prevention. I'll talk briefly about that at the very end. But what happened was, maybe 20 years ago, there's a drug developed called vemurafenib. And vemurafenib is a BRAF inhibitor. It blocks that oncogene, that mutation called BRAF. So these are patients that walked into our clinics over 15 years ago. This is actually a patient from MD Anderson, one from Peter McCollum in Australia. Australia's where I've seen some melanoma. They've watched sunburn. And what I'm showing you is a PET scan. Now, what is a PET scan? A PET scan is a metabolic study. And so, unlike CAT scans, we look at the size of the tumor. On a PET scan, you see the activity of the cancer, the metabolism, the actual energy. And in this patient here, we responded this as a melanoma. And these are the bones. His bones are literally riddled with melanoma. Here's a man from Houston. That's his liver. It's completely filled with melanoma. Those are metabolically growing active spots in his liver. He has some in his bone as well. These patients walked in, well, I take it back. They didn't walk in. They came in wheelchairs. They came in on stretchers. Because all of a sudden word got out, we have a drug that blocks BRAF. And everybody wanted the drug. Everybody wanted the drug. And why did they want the drug? Here's what happened. Within 6 weeks, this man's bone metastases, gone. This man's liver metastases, gone. 6 weeks. We could tell in 2, because all of a sudden they walked in. We've never seen this in medical oncology before. We gave it a name. The Lazarus effect, the rising from the dead. Because oncologically, in cancer medicine, this has never been seen before. And now we had a pill that would block a gene that makes cancers grow with complete eradication. Complete. Okay. Success. Well, we thought we're going to go out and close shop. Okay. Honestly, I wanted one day my dream is to put a sign on my door, go on fishing. Okay. Because they don't need me anymore. So I'm taking the same patient back, the one on the far left. Here he is. 3 months later, it's back. Okay. So despite our initial enthusiasm, many of these patients, not all of them, develop recurrent disease. And what was going on? So we went back to the machine. We took the tumors, we put them back into the machine. We say, is there something growing? Is there something developing, a new mutation that we need to block? Because tumors are smart. They find a way to bypass the block. So this is the blockade. It's a little this cartoon, but we know we can block BRAF. Okay. But take like this as a circuit. Okay. What's below BRAF? There's another gene called MEK. So they developed a method with a mutation to activate this part of the pathway below. So it was blocked here, but they didn't need this. Now they can activate it here and reactivate the pathway. So we're smart. We're oncologists. We said, let's develop a drug that blocks MEK. And today in oncology, if you're a cancer patient with the BRAF mutation, you get 2 drugs. You get one that blocks BRAF and one that blocks MEK. And this is the reason why. And this has transformed the field. So those failures are now much more sustainable. Now patients still fail, undoubtedly, from this targeted therapy, but the doublet has prevented that rapid recurrence we saw because now we have a dual inhibition. We have the upstream blockade, and now we block the downstream blockade. Now, do other activated steps develop? Yes, and there's still a challenge trying to figure this out. But this is how we got to the concept of 2 drugs, a MEK inhibitor and a RAF inhibitor together. Well, what about those other oncogenes? I mentioned on the melanomas that come from non-sun exposed parts of the body. And they have a gene activation called KIT, K-I-T. And at the time I was doing melanoma, I'm also doing sarcoma. We have a drug called Gleevec, imatinib, that blocks KIT. We've been using this for about 2 years. So I said, well, if it works in KIT mutant sarcoma, what about KIT mutant melanoma? Okay, an oncogene, a drug, a blocker. Just one of the first patients treated with Gleevec, and it was a melanoma and no sun. Here it is rising from below the toenail on the big toe. That is in PET scan again, the metabolic activity, the left foot. And he had multiple metastases going up the leg because that's how the tumor spread. We put him on a pill, no toxicity, 1 pill a day. He had a mutation in KIT. Within a month, you can see the melanomas are now going away. Within 2 months, they're completely gone. We're so surprised, we biopsied the areas, and what you're seeing here is no active cancer cells. What you see is melanin pigment. So this melanoma comes from the brown pigment. Tumor cells were eradicated, but the pigment, which is non-malignant, was left behind, but no cancer. The patient was cured. Again, another example of using genomics, using cancer sequencing, finding a gene, finding a drug, blocking the tumor, and curing the cancer. But you have to do the sequence. That's the key. Now I'm going to shift a little bit to the next seminal discovery. And everybody knows about immunotherapy. Okay, so here we have, what is immunotherapy? So immunotherapy is the activation of the cancer-fighting cell of the body called the T cell. And on the T cell, there are what we call immune breaks. And at the beginning of this field, I was working with a fellow named Jim Allison, who was at Memorial Sloan Kettering Cancer Center. And, I've been an oncologist for over 30 years. And the question to me always was, Dr. Schwarz, why cannot my immune system fight cancer? And before these drugs came into existence, the patient would bring a Bloomingdale, as a New Yorker, bag of pill bottles, throw them on the table, all vitamins and herbs, and say, Dr. Schwarz, which one can turn on my immune system? Well, most of them didn't really have an effect. And the question internally has been, why cannot our bodies fight cancer? Why cannot our immune system turn on against cancer? Well, the reason is, in the evolution of man, and I can't give you a reason why, there are these brakes that put the T cell to sleep. It's like a car. Your brake is on, it's not going to go. Release the brake, car goes, car moves, of course, and can you use the same idea to cure cancer? That's the idea. So we have these immune brakes, they're stop signs. So no, it's a stop signal. That's your foot on the brake. It's not going to do. It's not going to go. Your car's not going to go. But can we develop drugs that release the brake and, in fact, make that green light go on, and the T cell to go forward, and the T cell to fight cancer? So that's the concept. Okay, that's immune checkpoint therapy. Drugs that release the immune brakes on the T cell to fight cancer. The first one was called CTLA-4. You probably know that drug. It's called Yervoy, ipilimumab. The second one down here is a Keytruda, Opdivo, Vivo, pembrolizumab. Those are drugs that they target the second one. Now, the advantage of the first over the second. The first one, we think of Ipi, which is Yervoy. It's the master brake. It's the brake that activates the T cell, not just to fight cancer, but to go after every cell of the body. And that's a problem because we have toxicity. We know about that. The PD-1 brake is a little more cancer specific, so you avoid some of the toxicities. But at the beginning, all we had was this one. All we had at this one. And I remember the first patients we treated. This is a man who had melanoma in the back. We don't usually see this much anymore. Bad melanoma. Those masses are melanoma. He was placed on Yervoy, ipilimumab. And at week 12, it looked like the tumors were getting bigger, not smaller. And in fact, at this point, we thought it was a failure. So this man was having horrendous toxicity. Diarrhea, inflammation of the liver, effects on the adrenal gland. And we're thinking, what are we doing? We're torturing these patients, and the tumor's getting bigger. So we said, come back in 4 weeks, and the tumors began to look a little smaller. In fact, you can see this in the CAT scan. Tumor, this is all tumor. Week 16 began to look a little better. By week 72, it was gone. This man tumor never came back. So what was going on? At week 12, the T cells were activated and began to infiltrate the tumor. I used to think of like this as Lady Pac-Man. Lady Pac-Man cells infiltrating the cancer, making it look bigger and swelling. We had to biopsy the tumor to see the tumors were going away, but these T cells were eating the cancer apart. And that's what happens with these drugs. It takes a little time for this drug, a little faster for the Keytruda and Opdivo, but this is one of the first episodes. In fact, we were so disappointed early on, we almost gave up. But this one, so what happened was we went from ipilimumab and the toxicity, and then we went to PD-1. It took about 2 to 3 years to discover the second checkpoint. This wasn't immediate, obviously. There's again how science was able to find another break on the T cell. And this is a patient, one of the first patients who'd failed everything. This is what we used to do for these patients. We gave them a high dose interleukin-2. This patient actually already had ipilimumab. And this is a big tumor mass here, All that's cancer. This is a tumor in the liver, all cancer. And then what happens is on therapy, that big mass, it's a CAT scan of the chest. This all the normal lung goes, and the liver lesion dramatically improved. So now we had another big advance without the toxicities that were associated with the first class of drugs. Well, if one drug is good, maybe two drugs are better. This is the first report of combination. I'm showing you a couple things. This is called we call this a plot in which we look at not just regression. This is the shrinkage of the tumor, but how durable they are. This is not just the fact that tumors are shrinking, but how long a patient can stay on study. This is weeks and weeks of combination of Yervoy and Optivo. And then multiple masses on the chest wall. All those bumps there are cancer. And you can see they all go away by 12 weeks. So this is a lot faster than we showed with single agent IPI. Again, when you added PD-1, you get these dramatic regressions, not just regressions, but stability, because we'll measure that every couple of weeks to see how long they stay in remission. And this is one of those patients. So this is, again, a patient with extensive disease, bad cancer. Now we know we use combinations of therapy. So where are we? This is a publication, not to know how to interpret this. This is the 10-year survival. So we're over 10 years out from the first studies, decade. How well the patient's doing. Well, we didn't really anticipate this, but now at 10 years, this is the nivolumab and IPI, this is Nivo. At 10 years, called the Kaplan-Meier curve, half of our patients are alive cancer-free. They're cured. So we've gone in 10 years with a survival of 6 months to a survival in metastatic disease of 10 years at 50%. Now, I show this to my medical students. They go, Dr. Schwarz, that's great. What about the other 50%? Okay. We've made great strides, but we're not curing cancer in everybody. And that's still the challenge. How do we make it not just 50% in 10 years? How do we make it 100% in 10 years? And that's really something we need to work on. Just to review the toxicities, you add the second drug, the Yervoy. This is the percentage of patients with toxicities of the gastrointestinal type, diarrhea. Nivo by itself, which is the PD-1, much less. The question always comes up, do you need the second drug? Some people do, some people don't. That's a discussion with oncologists. Who gets doublets, who gets singlets? I'm not going to go into that. Maybe Dr. Mangel will bring it up, I'm not sure. But it's a challenge because when you add that second drug, ipilimumab, you're asking for trouble. You're going to get diarrhea. We have ways of control. Now imagine this 20 years ago. We had no idea. We didn't even know we were going to get diarrhea. We didn't know what we were going to do. We had those first patients therapy. We didn't know what to expect. Now those first weeks, it was a nightmare. Trying to figure out what we do. We'd have meetings every day. We get together. Okay, this guy's got diarrhea. What do we do for it? We give him Imodium. That didn't work. We give him syringe. You got to give him steroids. Well, you want to avoid steroids because steroids suppresses immunity. Pandora comes out of the box. We're putting Pandora in the box. Not good for the treatment, but good for the patient to avoid the diarrhea. So it's a challenge how to manage this. Which comes first? I mentioned now two things, targeted therapy and immunotherapy. Okay, so if you have a BRAF mutant melanoma, what do you take first? This is always a big question until a study was done. It was published by Atkins, a friend of ours, in Journal of Clinical Oncology. And what he did in the study is half the patients started immunotherapy first, and half the patients started that MEK-RAF combination. This is the BRAF and the TREMI, BRAF-MEK, IPI-Nivo, IPI-CTLA-4 PD-L1, randomized, equal. And if you progress, you crossed over. Bottom line is, in terms of 2-year, we don't have an update yet, 2-year survival, 72% alive with the combination getting immunotherapy first, and 52% alive getting BRAF targeted therapy first. This is for BRAF mutant melanoma, not for wild type. So again, the standard of care today is everybody who starts today with, you have a metastatic BRAF melanoma, you start with the combination of immunotherapy. If that doesn't work, then you go to the 2-drug therapy. We're giving it now in an earlier stage disease, that's advanced stage 4 disease. Now we're giving it to prevent recurrence after early stage resection. We call this adjuvant therapy. This is again a Kaplan-Meier curve, and you can see that when you compare Nivo to IPI, those that got the PD-1 versus the IPI, they did much better curability after surgical resection than those who got, Nivo was better than IPI, but overall compared to before, this is a huge advance. 80% alive at 2 years cancer-free with stage 2, stage 3 disease. Now we give it even for stage 2 disease. So earlier the disease now, as well as more advanced melanoma. Okay, we can treat melanoma. We're getting better, but we're not curing it. In half, it's better than I ever thought possible. But remember, we have melanoma as a preventable disease and it's summertime. And when you go to the beach, now I go to the beach, and you go to the beach and, it's Cleveland's cloudy. I really got here like 2.5 years ago. And you go to the beach and you forget, you leave that hat in the car and your sunscreen's behind and you go, oh my, and 2 hours later, the clouds are gone and, it's pretty hot, right? So you can't forget your sunscreen because, I think we always forget it. We can't forget it. We shouldn't forget it. I could say this summer, the Cancer Center, I don't have a slide on it. We have a program we've initiated in Cleveland and the surrounding counties called Stop the Burn. So if you're at a public pool, you may have noticed that we have kiosks working with L'Oreal, Poussey, and they supplied free sunscreen to all the patients in the Cuyahoga and all the surrounding counties. And it's a collaboration. We have an educational program to address the issue of making sunscreen available to all people in Cleveland and the surrounding counties of our catchment area. In fact, our catchment area, if they take this, all the counties, the Cancer Center represents 4.1 million people. So we have responsibility for a lot of people in this county, in these counties, not just the city of Cleveland proper. So research, I think we scratched the surface. We're doing a lot of research. How do you do it? It's almost my final slide. Old days, we take the melanoma and put it into a Waring blender. You make kind of a slurry and we'd analyze this. But you look at that's a tumor. You have millions of cells, they're all different. You have melanoma cells, you have surrounding cells, you have immune cells. It's a mixture of everything. It's a grab bag. What do we learn from that? Not a lot, except kind of the gestalt. Well, can we take every individual cell and make like a fruit cell? Can we individually analyze every single cell in the tumor? So we have technology that we're developing a case, which we can take the tumor, heat it to the level of the sun and explode it. But every single cell is preserved. Then we can take each cell on this map and analyze it individually. Now we begin to understand what happens in every single cell. They're all different and how they talk to each other. Well, the single cell RNA-seq. We're going to be doing this eventually in every cancer patient's case. I want to do this at every cancer patient in the United States. In fact, we had a big meeting yesterday, getting all the cancer centers together. We're 54 of us. There are 2 in Ohio, Cleveland, and there's 1 in Columbus. Can we get all the cancer centers across the country and do this technology on a wide scale level and make it available to every single patient and physician? And we analyze all these cells and find new targets, new pathways, and work with pharma to develop, or university to develop new drugs. That's my vision. We'll see, it's going to happen. I've got already the banks of Cleveland, I can't tell you which ones, are going to invest in this here in this community. And I have other corporations who are talking to me about making this a vision. So everybody has the potential to discover in their tumor what makes it grow. We know there's BRAF. We know there's PD-L1. There's got to be something else. So the other 50%, what are they? We're going to figure it out. And we're going to figure it out here in this cancer center. So more research needs to be done. We're advancing the tumor. We got to look at the tumor microenvironment. I think we have new technologies we can use. Everybody should be in a clinical trial. I think that's important. If there's a clinical trial available to answer these questions, what is the next drug? What's beyond PD-1? What are the next targets? And of course, we need to invest in prevention because Ben Franklin said, prevention is worth a pound of cure. He said that 250 years ago. Now who's talking about? Fire department. Okay. He built the fire department, preventing fires. But we can say that applies to cancer. We have to prevent melanoma. It's not that difficult when you educate people what it takes. Okay, I'm going to stop there.
Thank you so much, Dr. Schwarz, for that talk. That was really nice, and that gives us a very good perspective into what melanoma, where we have come in melanoma so far.